Thanks, everyone. Happy to be here. I have to say this is the coolest backdrop I've ever presented against, so it's exciting for me. So my talk, I'm just going to give you a brief introduction to our company, our philosophy on quantum computing, and our path towards scaling our systems and some of the challenges that we see. So Quantinuum, we have over 500 employees across the globe, 8 different offices. We have a large number of PhDs who work for us, lots of patents, and we pride ourselves on getting out lots of scientific papers. So that's really how we judge ourselves at the moment. When we think about quantum computing, we don't just look at the hardware, we look across the full stack. So we have application solutions ranging from Quanto, which is a quantum chemistry package. We have products in the middleware like Ticket, that is a circuit optimization toolkit. We have Quantinuum Nexus, which is a hub to bring our users together. And then at the lowest layer, we have the hardware. So it's not just one thing, it's bringing everything together when we think about scaling and we look at the full stack required to really realize the value of quantum computing. So a little bit about our hardware. We're a trapped ion quantum computing company. So we use the QCCD architecture, which was developed at NIST. So this really means that at the base layer, we have a trap that's fabricated. And we use this to confine ions that are our qubits. So we can have dedicated gate zones, which you see in the image here. The blue are the gate zones. And we can use the electrodes on the bottom to move ions in arbitrary configurations. And we can also confine them radially using those 2 green rods that you see. So this architecture is really advantageous for us because it allows us to have full configurability, as well as all-to-all connectivity, bringing any 2 arbitrary qubits together. But it also allows for very high fidelity operations. So in our trap, the ytterbium is our qubit, and we also have cooling ions that are shown in blue here. So this is really the basis of what we're working on. And then in terms of entangling, we use lasers. So really what we're looking at is scaling this architecture to larger number of ions, or larger number of qubits. So this is our pathway. And this really, what you're seeing here is the transition from where we are right now. So we have H1 and H2, which have 20 and 56 qubits respectively, all the way up to 2029, when we'll have Apollo, which will have thousands of physical qubits and hundreds of logical qubits. So the challenge here, or the opportunity in front of us, is to really expand the chip, and we work with vendors like Infineon to do this, really bringing in their expertise on manufacturability and how we do this robustly. So this year, you'll see when we'll be releasing Helios, and this will be our first step into junction transport. Why this is key is really to scale trapped ions. The key is moving from where we've traditionally had these 1D traps, where we're moving ions in a line, to now to 2 dimensions. So this really gives us what we need in order to scale and to improve the speeds in our system. So Helios will be released later this year with 96 qubits. Then we'll go to Sol, where we have a grid architecture, and then to Apollo later at the end of the decade, which is where we really see having to scale our solution. And we're looking really to manufacture that system. So the strategy to scale trapped ion quantum computers really in 2 pieces here. One is hardware improvements. So it's that 2D grid architecture, but maintaining the number of control signals needed to do that. So being very reasonable in how the analog systems have to scale with the architecture, as well as improving our fidelity, speed, and coherence times, and integrating photonics into the actual system. As well as on the other side is reducing the resources needed to achieve fault-tolerant quantum computing. So that means looking at efficient, high-rate, low-density LDPC codes, leveraging error detection and even distance codes when practical, and utilizing our long coherence time to implement better decoders. So this is just showing here where we have demonstrated dual species transport through a junction. Unfortunately, the image doesn't work here, but you can use your imagination that dot there is able to move to all four corners of that junction. And we can do that with low heating, which is important. So that means it doesn't degrade the fidelity of the qubit as we move it through that junction. Also, we've demonstrated what we call the we've demonstrated a method where we can scale the analog electronics without having to be one-to-one with the number of electrodes. So what we do here is we tie the electrodes together. We have a fixed number of AWG channels, and we can use this method called the C2LR method. And again, the animation doesn't work here, but you would see that you can swap the ions in the lower left and upper right corner very efficiently with a small number of signals just by utilizing one control signal in the middle. And so this means we can do this with a low overhead in terms of the electronics required and to lead to efficient sorting in a grid trap, which is really key for us. The other thing that we look at is we can't just buy commercial electronics. That would be very expensive. That's not scalable. So we're really on this path towards, we started, in that upper left-hand corner. We've designed custom racks and rack-mounted electronics. We brought that in-house, and then the next step will be able to integrate that onto the chip. So all of this leads towards more reproducible, smaller scale systems. We're also looking at integrated photonics. So we work with a lot of vendors in this, or a lot of partners, like Sandia, New Mexico, looking at low loss waveguides, gate couplers, metamaterials, metasurfaces, improved beam design, all to efficiently use the lasers on our system. So we really bring them where they're needed on the system to produce better scalability in the future. So that kind of covers the hardware piece, but we also do a lot on the fault tolerance side. So this is just showing kind of pathway of all the different results that we've had at Quantinuum on this pathway towards fault tolerance. Starting with our first demonstration of back in 2022, where we showed, or actually 2021, where we showed real-time error correction of logical qubits. Better fidelity than logical with the CNOT and better spam than physical. Magic state distillation with CR. So number of demonstrations. And more recently, we've been looking at these 4D surface codes on our computers, as well as the QCD or the QLDPC codes. And we've also done some demonstrations that probably you've seen with Microsoft recently, demonstrating reliable logical qubits. And so all this is coming together really to push the frontiers. And I will point out recently we have a hybrid integration of one of our systems at RIKEN, where we've deployed an H1 system integrated with the Fugaku supercomputer. Thanks everyone for your time. I appreciate the opportunity to present here.